Hello students, in this video let us learn about retarded potentials. So in the last class we tried to understand about inhomogeneous wave equations. What are inhomogeneous wave equations? It is given by box square V is equal to minus rho by epsilon 0 and box square A which is equal to minus mu 0 G. Here V is the scalar potential, A is the vector potential, rho is the current density per volume and rho is the charge density per volume and J is the current density. So these equations are actually a summarized form of Maxwell's equations with the Lorentz gauge conditions applied. So every concept that we have in the Maxwell's equation, we have summarized them in this inhomogeneous wave equation. Now, what are the solutions of these equations? These are actually differential equations. Box square involves differentiation with respect to space as well as time. So these equations have a solution and the solutions must say about potentials, right? If we have a differential equation, suppose say d square f by dx square equal to x square plus 2, its solution means what is f of x? Similarly, we have some differential equation in homogeneous wave equations here, and these equations, the solutions of these equations will give us the scalar potential as well as the vector potential. First of all, let us think about the solutions of these wave equations in static case. So in the static case, these wave equations, which are del square minus mu 0 epsilon 0 dou square by dou t square of V is equal to minus rho by epsilon 0 and del square minus mu 0 epsilon 0 dou square by dou t square of A which is equal to minus mu 0 J. So these are the inhomogeneous wave equations as we know, and in the static case there is no dependence on time, and these equations can be simply reduced into del square V is equal to minus rho by epsilon 0 and del square A equal to minus mu 0 G. So the first equation, maybe you are familiar with the first equation, which is the Paulson's equation. So these are the equations in the static case. And what are the solutions of these equations? It can be find that the solutions of these equations are given by V of r bar is equal to 1 by 4 pi epsilon 0 integral rho of r bar dash divided by r d tau dash. So this equation is familiar to you, right? Maybe you are aware with the equation potential is equal to 1 by 4 pi epsilon 0 q by r. Haven't you seen this equation in your basic classes, in your lower classes? So this equation is just the same as the new equation. This is the potential due to a point charge which has a charge q. Normally charge distribution might not be a point, it will be spread over a whole volume. So in that case we cannot simply take q as our charge. In that case we take q equal to integral of the charge density over whole volume. Integral rho d tau should be the total charge. Now since the distribution is spread throughout the volume, we should also consider the distance to be as within its integral. We cannot separate this r out of this integral. You will understand that concept when we go further into this concept, further into these theories. So as of now, as we have seen here, inhomogeneous wave equation in the case of a static system will be Paulson's equation, and the solution of the Paulson's equation is given by V equal to 1 by 4 pi epsilon 0 integral rho d tau by r. Integral rho d tau is simply Q. So this is your familiar equation and this is a more generalized equation. So before moving on with this topic, let me make some important points clear to you. So throughout these lectures, in the coming classes, we will be using different types of vectors, different names for different vectors. Mainly, in order to represent position, we will be using three different standard vectors. One will be r bar, second one will be r bar dash, and the third one will be again r bar. I will call this curly r. So we will have three different vectors, position vectors, and each of these vectors represent three different concepts. So let me familiarize you with that first. Suppose we have an origin here. Then vector r bar is the position vector of the point which is under consideration. Suppose you need to calculate the potential at a point, or you need to calculate the electric field at a point, or the vector potential at a particular point. So this any point, any random point in the space is denoted by vector r bar. Vector r bar will connect the origin and the random point in the space where we calculate potential or field. Now the second vector r bar dash is the position vector of charge, the position vector of the place where the charge is situated. If it is a distribution of charge, we know charge is distributed over a very large volume, then each of these unit volumes or each of these small volumes is denoted by r bar dash. So if we are considering this small volume, r bar dash is the vector towards that particular volume. If you are considering another small volume here where charge is situated, r bar dash will be the vector towards that part. Now we have the curly r. Curly r is the vector from the charge up to the point. So you can see it here. Curly r bar connects the charge to the random point considered. So clearly, because of the vector addition rules, we can say that curly r bar is equal to r bar minus r bar dash. So there are three different position vectors that we will be using in this class, and they are r bar dash and curly r bar. If we put a dash here, normally that means that we are considering the position where charge is situated. For example, d tau dash means the small volume element where the charge is situated. R bar simply is the position vector of any random point, and curly r bar is the position or vector connecting the volume element of charge with the random point considered in the space. So be thorough with these three vectors, do not get confused with these three vectors. So as we have written here, this solution, here two different r bars are coming, not two, actually three r bars are coming here. So look at that r bar, V of r bar. That means we are calculating the scalar potential at the point P. So this is our origin. So there we are calculating V of r bar. And for that we need to consider the charge at r bar dash. So it is not r bar, here it is r bar dash because charge is not situated at r bar, right? Charge is situated at r bar dash. So see here, for that we consider rho of r bar dash. And finally, in the denominator we have the distance between the charge and the position of the point, random point. That is actually given by curly r, this r. Here potential is determined by the distance between the charge and the point. Whatever be the position of the origin, the potential will be independent of that origin. So if it is here, origin is here or there, that is not determining the value of potential. Origin can be chosen randomly. Even then, we consider the distance between the charge and the point where potential is calculated. So that is why we are putting here a curly r, magnitude of the curly r, which is the distance between charge and the point where we are calculating the potential. So we have three different vector r here. First one is the position vector of the point P, second one is the position vector of charge, and the third one is the distance between charge and the point P. So while you write the equation, keep in mind what each of these position vectors mean and try to be accurate while putting each notation. Be thorough with r bar dash and curly r. Now moving on with our concept of potential. As we have said, the solution of the first equation in the case of a static case, the inhomogeneous wave equation, will yield you V equal to 1 by 4 pi epsilon 0 integral rho d tau by r. Here also we put a dash to denote that charge is situated there. Similarly, the second equation, the solution of the second equation in the case of a static case will yield you the equation for vector potential, and it is given by a bar of r bar is equal to mu 0 by 4 pi into integral j bar of r bar dash divided by r into d tau dash. Here again you notice we have used three different position vectors, r bar dash and curly r. We are calculating the potential at r bar. For that we consider the charge density, the current density at r bar dash, and we finally need to consider the distance between the current density, the point where the current is passing, and the position vector. So three different r's are coming here, r bar dash and curly r bar. So as I have mentioned, these two equations are the solutions of inhomogeneous wave equations in a static case. That means if the charge is not dependent on time or the current is not dependent on time and there are no factors that are varying with respect to time, then these equations will hold good. But what will happen if the system is charge dependent? What will happen in an electrodynamic system? Are these equations correct? Should we make any change in these equations if there is any time dependence? Okay, let us think about that. So we know that from Einstein's theory of general relativity, we know that nothing can travel faster than light, right? So nothing travel faster than light. So that means even the electromagnetic waves, the electric fields or magnetic fields or changes in potential or any other physical quantity, it is impossible for them to travel faster than light. So we can use that concept to modify our equations for vector potential and scalar potential. So let us assume that the given charge configuration is dependent on time. That means the charge within this volume is varying. It is time dependent. So suppose we have charge rho, which is a function of both position vector r bar dash as well as time. So here we have, suppose maybe this charge might be moving within this volume, or this volume as a whole will be moving in the space, so that there is a change with respect to time. So all these kinds of motions and change actually constitute an electrodynamic system. That means sometimes charge is flowing through the system. Sometimes the charge will increase and decrease in the system. Sometimes this whole volume might be moving through the space, and that will cause some effect on the potential, scalar potential as well as vector potential, right? So what will be that change? What will be that difference in potential? So we know that electromagnetic information or electromagnetic news, even they cannot exceed the speed of light. By electromagnetic news, I mean that the potential, field, or any other physically relevant quantities that can be measured at a distance. So even that quantity cannot exceed the speed of light according to Einstein's theory. So suppose this charge configuration is suddenly experiencing a change, and how fast that change or that electromagnetic news can reach a farther point. Can you think about that? So my question is this: in this charge configuration, the charge is changing with respect to time. Suppose you think that all of a sudden this charge is being created here. Would we know the influence of this charge at a faraway point P instantaneously at that time itself? If it is not known instantaneously, then when can we know that this charge is being created? So for a better understanding, I will give you the example of sun. So you know about our solar system. We know that Earth is situated at about 1 astronomical unit distant from the sun. So the light that travels from the sun reaches Earth after 8.33 minutes. So these concepts must be already familiar for you. So what will happen if all of a sudden sun disappears here? Will we know it on the Earth right away, or will it take some time for the sun as seen from the Earth to disappear? So we know that the sun that we see right now is 8.33 minutes older. So if you look up at the sky right now, the sun that you see in the sky is not the sun that is present there right now. That sun has been present there 8.33 minutes ago. So if the sun goes off right now, switches off right now, you will know about it only in 8.33 minutes. There can be no device on the Earth that can immediately detect that sun has gone off, because these electromagnetic radiations or the light from the sun reaches Earth taking the speed of light, c. Similarly, many of the stars that we see in the sky during night, some of them have gone extinct. They have gone extinct maybe some millions of years ago, but we are still seeing that star because the waves from that star, the electromagnetic waves, the light from that star reaches Earth only at this time. So similarly, the same concept holds here in the case of time-dependent potentials, time-dependent charge configurations. So if this charge configuration is both dependent on position and time, the potential that is experienced at a faraway point P is not due to the charge configuration of right now. It is due to a charge configuration of a little time before. So if this charge configuration is all of a sudden changing, then the point P will experience that change a little time later, because this potential variation or the electromagnetic news obtained from this variation of charges and currents will take some time, will propagate with the speed of c, and will reach the point P later. So from the P, for an observer at P, the charge configuration that determines the value of potentials and fields, suppose P of r bar, A of r bar, are all measured at the point P, and we are looking at this charge configuration which is time dependent. And right now when we measure the potential V or A bar, or measure the fields, electric field and magnetic field, those fields are determined by charges that was present in this configuration a little time before. I call that time retarded time TR. So why we consider a retarded time potential? So the charges at a retarded time, because at the point P we experience the potential, vector potential and the scalar potential because of the charge that was present at a little time ago. Just like we see the sun, which is present 8.33 minutes ago at its position. Now, for an observer at point P, he will experience the potential due to the charge configuration that was present here a little time ago. So if right now this charge has another value, another configuration, another existence, then the P will experience that a little time later only, when this electromagnetic news, when this potential variation slowly reaches the point P, P will come to know about this variation. So what will be this retarded time? Suppose we represent the time that is right now as T. Then we know that if curly r is the distance between the charge configuration and the point P, we know curly r represents the vector between the charge and the point P. How much time will it take for an electromagnetic radiation to move from r bar dash up to the point P? So we know electromagnetic radiations travel with speed of light, which is c, and in order to travel an r distance, how much time it will take? Distance divided by speed. So r by c is the time taken by any field, any electromagnetic radiation to move from this point up to P. So if T is the time at right now, then T minus R by C will be our retarded time. So the charge configuration that was present at this point at T minus R by C time will be experienced by this point P right now. So for this point P, let me again make it clear for you in another way. For this point P, if it is looking at a charge configuration, the charge configuration right now doesn't matter. The charge configuration a little time earlier is actually contributing to the potential at the point P. And how much time earlier? We have to subtract the time taken for the electromagnetic news to travel, and that time is R by C. So T minus R by C should be the proper time, the retarded time that should be considered at the point P. So for any observer at point P, he will be experiencing the charges, the potential and field due to a charge in this configuration at a retarded time Tr. So how should I modify the equations for scalar and vector potentials in the case of an electrodynamic system? So as we know, in the case of an electrodynamic system, potential and field are time dependent. So V is not just a function of position alone, it is a function of time. Similarly, the vector potential is also a function of position and time. So what will be V of r bar comma t? It will be 1 by 4 pi epsilon 0 integral rho of r bar dash at the time Tr, right? The charges at the time of Tr has to be considered to calculate the potential at time T. Here T is placed and here Tr is placed. Why is it different? Because charge configuration at the time Tr determines the potential at time T at the position r bar. Once again, the charge density at the position r bar dash at the time Tr determines the potential at r bar at the time T. Why is there a difference in time? This difference in time is taken for this potential, this change in potential to reach that point. So from here we consider the charge at r bar dash comma Tr. So this charge configuration will be determining the potential at P at position of which is r bar at the time T. So the difference in time is the time taken for this news to reach the point P, the time taken to travel that distance for an electromagnetic wave or any other electromagnetic information moving at the speed of light. So this should be our new equation divided by curly R. So this should be our modified equation in the case of an electrodynamic system. So what about vector potential? It will be mu 0 by 4 pi into integral j bar of r bar dash comma t r divided by curly r theta dash. Here also the integration is over the Boolean. So here also you please notice that the current density should be considered at the point r bar dash at the time tr, but the vector potential we calculate at the point r bar at the time t. The difference in time is due to the fact that if the current is changing with respect to time, it will take a little time to reach the point P where we measure the vector potential. So this is the concept of retarded potential. We call this current, these integrals as these scalar and vector potential as retarded potential because we calculate these integrands as in a retarded time. So that is why they are called retarded potentials. So what are retarded potentials? They just represent the scalar potential and vector potential of an electrodynamic system, of a time dependent system, and they are actually calculated in a retarded time. That because we know any information, even an electromagnetic news, takes some time to travel, and r by c time is taken for any electromagnetic information to travel through space. So that is actually considered in calculating the real times involved in these equations. So in the next class, we will put a sound theoretical base for these arguments. I have just stated some arguments in order to put forward these equations of retarded potentials. These are actually our own logics written in the mathematical formulation. In the next class, we will actually try to prove that these equations are true. These equations holds good. So as of now, I hope that this concept of retarded potential is clear for you. Just be thorough with different terms and vectors that we use here. Just try to differentiate between time t, which is the time at right now, and the retarded time, which is a little time earlier, which is t minus r by c. I hope this portion is clear for you. Thank you.